we saw in a previous video, where we defined surface integrals and the general surface integral to be of the following form, right? Where the integrand is the function f of x, y, and z. D capital S is the differential element of surface area. And we showed in that video that that element was equal to the following magnitude of the cross product of these two vectors. Again, this assumes that the surface is given parametrically in this form, okay? So what I wanted to do in this video, very briefly, is just talk a little bit about this cross product right here, okay? So let's do this. Let's consider the surface given parametrically by R of U and V. Okay. It's the same, I don't know, maybe just a big sweeping surface, something like that. Okay. And let's say that here's our vector U, or R rather, and say it points to this point right here. Again, what I'm going to do is, what I'm going to say is, let the vector R of U and V sub 0 be that particular arrow. In other words, let the second coordinate V be fixed at V sub 0. Then what's going to happen is that vector is actually going to represent a curve on the surface. That curve might look something like this. Okay, and I'll just make a note over here, right, that V on that curve, V equals V sub 0, but U still varies. Okay, like that. We could call the curve C1 if you like. Okay, but think of that as like a vector value function. U varies, but V sub 0 is a fixed number. And so what's going to happen is that vector value function is actually going to sweep out, or going to trace out that curve. Maybe it looks something like this. Okay. On the other hand, if I let U be fixed at some number and I let V vary instead, now that might look something like this. Okay, and I'll make a note on this curve. U equals U sub 0. Okay, but V can still vary. Okay, maybe I'll call that curve C2, like that. Okay, now from our work in previous classes, right, what we can do is interpret these partial derivatives in the context of tangent vectors. For example, at this point right here, along C1, the tangent vector would look like this, and we would refer to that as the partial of R with respect to U. That would give me a tangent vector right there at that particular point. Whereas on sorry, that was C1, this is C2. Along C2, in a similar way, we would call this tangent vector the partial of R with respect to V. Okay, so see what I'm doing? Again, I'm interpreting these in the context of tangent vectors. Okay, all right, well, so if I cross these two vectors together, which is exactly what you have in the rectangle right here, you're going to get a third vector. Let's change the color. Let's make that green. Okay, and what's going to happen is that vector is going to be a normal vector to the surface. First, let me write that down, and then I'll tell you why. So notice that C1 and C2 lie on the surface. Okay, they lie on the surface. Notice that those tangent vectors are tangent to the surface at the point right here. Okay, so the green vector is perpendicular to both of those tangent vectors, and therefore we say is perpendicular or orthogonal to the surface itself. So we could actually write the differential element of surface area like this. Shorthand, if you will. Okay, shorthand. So once again, what I'm doing is I'm holding one of the variables fixed. Either I'm going to hold V fixed at V sub 0, in which case the vector will trace out a curve C1, something like this, or I hold U to be fixed, in which case V will vary. This should be a U sub 0 right here. It looks like V sub 0. Sorry about that, gang. That should be a U sub 0. Okay. But either way, those curves are actually traced out on the surface. They lie on the surface, those two curves. The vectors partial of r with respect to v and partial of r with respect to u are both tangent to those curves, okay? In particular, at that point right there. Interesting thing also, again, all those two vectors actually make a parallelogram, right? They're adjacent sides of a parallelogram. Looks like a reminiscent of tangent planes, which you covered in previous course or probably previous section of your multivariable calculus class, okay? In any event, notice that our green vector is orthogonal to that plane, which is orthogonal also to the surface. This will come in handy, I think, when you're solving surface integrals of vector fields, for example. And maybe we'll make another video of some examples of those.